Tonight, we turn our gaze gently toward the radiant heart of our solar system, a celestial body that has, for countless millennia, dominated our sky and, indeed, our very lives. It is the sun, that eternal furnace, burning with a ferocious and mesmerizing glow at the very core of our cosmic neighborhood. But now, as our human ingenuity has pushed the boundaries of technology far beyond the wildest dreams of our ancestors, we find ourselves with the ability to delve into the deepest, most subtle processes, both within and around our neighboring yellow dwarf star. We can journey, deeper than ever before, through its vast, energetic atmosphere, exploring phenomena that, I believe, you will find utterly fascinating. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. As we begin this tranquil exploration, let us imagine ourselves like one might approach a magnificent fruit, by starting with its outermost layers and slowly, carefully working our way inward. Our initial destination, then, is the very edge of the sun's atmospheric embrace, the corona. Consider, if you will, this ethereal image captured by the Solar Dynamics Observatory, or SDO. This NASA mission, a marvel of engineering, was launched with purpose, back in the distant February of 2010. Its grand ambition to gain a deeper understanding of the subtle solar variations that constantly influence life here on Earth, and indeed, our intricate technological systems. This grand undertaking was to be achieved by meticulously studying the dynamic surface and the ever-changing atmosphere of our star across a wide array of different electromagnetic wavelengths. By carefully observing light far beyond the narrow band of what our human eyes can perceive, the visible spectrum, NASA scientists were able to unveil details that are normally entirely invisible to us. These hidden intricacies, crucial to our evolving comprehension of the sun, were brought into sharp focus. This particular image, for instance, was captured using a precise wavelength of 19.3 nanometers. This represents light found deep within the extreme ultraviolet region of the electromagnetic spectrum. At this wavelength, corresponding to an astonishing color temperature of 1 million Kelvin, we are granted a clear, unobstructed view of the higher reaches of the sun's majestic corona. It's a curious fact, isn't it, that the sun's corona, this incandescent crown of plasma, can, on very rare occasions, be glimpsed even by the unaided human eye. Such fleeting opportunities arise only during the breathtaking spectacle of a total solar eclipse. In these precious moments, when our moon, in a dance of cosmic precision, perfectly aligns itself between the Earth and the sun, the central, intensely bright disk, known as the photosphere, is entirely blocked. For a brief, precious period, the radiant exterior of the corona is unveiled, shimmering with an otherworldly glow. While this naked eye view is undoubtedly a profoundly moving and unforgettable sight, the corona revealed during an eclipse is still nowhere near as detailed or as scientifically informative as the images captured by the SDO. The observatory's sophisticated instruments provide an invaluable tool for scientific study, allowing researchers to peer into the subtle structures and dynamics of this outermost atmospheric layer. But let us now journey a little deeper, moving beyond the corona's outer reaches, to explore features of the sun that lie just beneath this luminous crown. As we shift our perspective to a color temperature of 20 million Kelvin, intensely vivid spots begin to emerge. These are the telltale signs of events known as solar flares. Imagine, if you will, the sheer cosmic drama unfolding in footage from a particularly active week for flares, like one captured back in August of 2022. These phenomena, to many, are both terrifying in their raw power and utterly hypnotizing in their visual splendor. Solar flares are colossal explosions where the sun, with an almost unimaginable force, spews out an immense quantity of electromagnetic radiation. They are born from the intricate dance of magnetic fields, which, within the sun's turbulent plasma, cross, distort, and then rapidly reorganize themselves, releasing vast amounts of stored energy in an instant. This tumultuous activity, this cosmic ballad of magnetic forces, is ultimately rooted in the chaotic, dynamic nature of the plasma that constitutes the sun itself. Yet, solar flares are not the only dramatic feature of the sun's atmosphere that vents radiation into space. Consider also coronal holes. These are indicated in extreme ultraviolet light by darker regions on the sun's disk. Coronal holes are another fascinating, albeit somewhat more subtle, feature. They represent areas of cooler, less dense plasma. What makes them unique is their magnetically open nature. This means that, unlike the closed loops of magnetic field lines that typically arc back down to the sun's surface, the field lines in coronal holes extend outward, traveling across the vast expanse of the solar system. These open pathways provide an easy escape route for solar wind particles, allowing them to stream more readily into space. When these energetic solar winds are directed toward, and subsequently collide with, Earth's protective magnetosphere, they trigger a breathtaking celestial display, the beautiful aurora lights, dancing across the night sky in our planet's polar regions. Observing these captivating features with ultraviolet light grants us a far clearer, more detailed view of the intricate dynamics at play in the sun's outer layers. Indeed, the non-visible spectrum of light is an utterly incredible tool, unlocking a universe of detail that would otherwise remain hidden. There are so many distinct features in the sun's outer layers awaiting our tranquil observation. Picture, for instance, solar filaments, also known as solar prominences. These are magnificent, arching loops of plasma that gracefully rise from the sun's blazing surface. These enormous loops are so vast, so truly gargantuan, that our entire Earth would appear as nothing more than a tiny, insignificant speck in comparison. They can stretch for hundreds of thousands of kilometers into the cold, silent void of space. While some can form in as little as a single day, a stable prominence, held aloft by the sun's powerful magnetic fields, can persist within the corona for several months, a testament to the enduring forces at play. Observe, in this example, a solar prominence as it majestically snakes its way out of the photosphere and ascends into the sun's expansive atmosphere. Though this video is sped up, compressing minutes into mere seconds, when you fully grasp the immense scale of the prominence, it becomes strikingly clear just how swiftly, and with what incredible power, the sun's intense magnetic fields are propelling this incandescent material. Here's a curious fact you might not have known about the sun's atmosphere: it sometimes rains there. Not all of the superheated, charged plasma, launched into the sun's corona, continues its outward journey across the solar system. A portion of it lingers, getting trapped within the magnetic field lines, cooling gradually until it eventually cascades back toward the sun's surface like a shining, fiery rain. This coronal rain is undeniably a beautiful spectacle to behold, but it is, of course, best observed from a very safe distance. Even in its cool state, it still maintains temperatures in the millions of degrees. However, falling gently back to the sun's surface is only the fate of some of this solar plasma. This is where any comparison to Earth's weather systems quite dramatically breaks down. After all, on Earth, clouds do not suddenly crack and violently fire into space, like a released elastic band. But on the sun, thanks to its tightly wound and immensely powerful magnetic fields, such explosive events are a regular occurrence. Observe, in this mesmerizing time lapse, a coronal mass ejection or CME. Watch as the colossal structure slowly forms in the lower left quadrant of the sun's disk, gathering energy and mass over a period of time. Then, eventually, it snaps with an almost palpable force, sending billions of tons of superheated plasma hurtling out across the solar system. Even with Earth's protective magnetic field, a direct hit from one of these powerful ejections could prove devastating for our sensitive satellites and our interconnected electrical grids. All of these magnificent structures, from the subtle dance of coronal rain to the explosive power of CMEs, are meticulously imaged by the SDO. This particular view utilizes a 30 nanometer wavelength of light, corresponding, once again, to the extreme ultraviolet portion of the electromagnetic spectrum. Timing, it must be noted, is of paramount importance when attempting to capture these transient features, as their frequency varies significantly from year to year. In fact, the appearance and intensity of each solar structure are intricately dependent on the overall solar activity of the Sun, which fluctuates in a cyclical pattern, oscillating around an approximately 11-year solar cycle. But there is still so much more to learn, so many more layers to peel back. Just as employing both visible and ultraviolet light reveals different aspects of the same solar feature, utilizing two distinct wavelengths of non-visible light can also prove to be incredibly eye-opening. To illustrate this point, let us consider these two striking images of the Sun's corona, both captured over precisely the same time period. The first image, viewed at a color temperature of 600,000 Kelvin, beautifully depicts the quiet corona, showcasing the graceful arcs and intricate pathways of coronal loops. The second image, however, captured at a much higher color temperature of 2 million Kelvin, dramatically highlights the significantly hotter, more active regions of the corona. The stark contrast between these two images underscores the profound importance of employing diverse observational approaches when investigating our star. What might, at first glance, appear to be a singular, monolithic solar phenomenon can, through the lens of different wavelengths, be revealed as a complex, intricately intertwined chain of events. And yet, we still haven't, technically speaking, made it entirely through the Sun's atmosphere. Moving further inward, let us now focus our attention on another image, also produced by the SDO, this time utilizing a 160 nanometer wavelength of light. This view brings into focus the transition region. The transition region is a remarkably thin layer, nestled between the expansive corona above and the chromosphere, which is the lowest layer of the Sun's atmosphere below. It is, in cosmic terms, a very shallow layer, spanning a mere 100 kilometers in thickness. Within this critical boundary, the thermal temperature of the Sun undergoes a dramatic and astonishing escalation, rising sharply from approximately 8,000 Kelvin to a staggering 500,000 Kelvin. To offer an earthly comparison, the fiercely scalding lava erupting from a Hawaiian volcano reaches temperatures of about 170 degrees Celsius, or roughly 1443 Kelvin. The temperature at the lower, deeper end of the Sun's transition region is almost 6 times hotter than this terrestrial inferno. And at the upper end of the transition region, the temperature soars to more than 346 times hotter. Traveling even deeper into the Sun's atmospheric layers, we find ourselves immersed in the chromosphere. This is the final atmospheric layer before we finally reach the Sun's visible surface itself, the photosphere. Imaged here using 170 nanometer ultraviolet light, the chromosphere is estimated to be approximately 700 kilometers thick. Upon closer inspection of the chromosphere, we can identify some truly mesmerizing features known as spicules. These appear like long, wavy blades of grass, swaying gently in an unseen cosmic wind. These elongated jets of plasma shoot upwards, with incredible velocity, from the Sun's surface, reaching speeds of up to 100 kilometers per second. That's approximately 282 times faster than the speed of sound here on Earth. They can extend to lengths of nearly 10,000 kilometers, making them over a kilometer taller than even the mighty Mount Everest. These ephemeral structures form and vanish in a remarkably short period, typically lasting only about 5 to 10 minutes on average. For a considerable time, the precise processes behind the formation of these spicules remained largely unknown and were a subject of intense scientific debate. It wasn't immediately clear how magnetically charged particles could possibly escape the sun's powerful magnetic fields at that atmospheric level. That mystery persisted until 2017, when a dedicated team of scientists working on an extremely detailed computational model of spicules made a crucial discovery. Their origins must be intricately related to neutral particles. Scientists had not initially incorporated neutral particles into their models of the sun, as they had not believed these non-charged elements would significantly affect the motion of the magnetically charged particles. However, once these neutral particles were included in the simulations, it transpired that they imparted an unexpected buoyancy to the charged particles. This newfound buoyancy provided the necessary lift, allowing the charged plasma to overcome the sun's gravitational and magnetic pull and shoot upwards into the spectacular spicules we observe. Descending even further now, through the sun's lower atmosphere, we eventually reach the photosphere. This is, in essence, the visible surface of the sun itself, and it is best imaged using the familiar spectrum of visible light. While the edge of the photosphere often appears sharp and precisely defined to our naked eye, this is, in reality, merely an illusion, a consequence of the immense distance separating us from the sun. The sun itself is not solid at all. In fact, it is far too hot for matter to exist in a solid, liquid, or even a conventional gaseous state in any region of the sun. Instead, all of the sun's material exists as plasma, often referred to as the fourth state of matter, and it is estimated to comprise a staggering 99.9% of all visible matter in the entire universe. Plasmas tend to behave in many ways much like gases. With one crucial distinction, they are composed of a volatile mixture of ionized atoms and free electrons, constantly interacting and moving. The photosphere, this outermost visible layer, is approximately 400 kilometers thick. It is not, as its appearance might suggest, a fixed, solid boundary of the sun. And, regrettably, it represents the deepest layer of our star that scientists can directly measure and observe. Upon a closer, more detailed look at the photosphere, you might begin to notice some dark spots, particularly on the left-hand side of this image. These intriguing features are known as sunspots. They appear darker than the surrounding parts of the photosphere, simply because they are cooler in temperature. Though cooler is a relative term in this scorching environment. Unlike coronal holes, sunspots form in regions where the magnetic fields are particularly powerful and concentrated. Here, heat becomes trapped beneath the photosphere due to a localized decrease in convection within these areas. When we compare this visible, light image of the sun, revealing its sunspots, to a previous image taken using extreme ultraviolet light over the exact same period, a compelling connection begins to emerge between sunspots and solar flares. The captivating, explosive solar flares and the darker, cooler sunspots consistently coincide at the very same locations on the sun's surface. From this observation, peering beneath the surface, it becomes clear that one phenomenon must, in some fundamental way, lead to the other. Now, let us take an even closer, more magnified look at some similar sunspots. This particular image was captured by the Swedish Solar Telescope, an instrument based right here on Earth, utilizing a visible light wavelength of approximately 400 nanometers. Adjacent to and surrounding these prominent sunspots, the photosphere appears saturated with endlessly shifting, jagged, edged cells. Visually, this sight is not dissimilar to the way lava cools and cracks on Earth, forming intricate patterns. However, these solar cells are immense, each roughly 1,000 kilometers wide, and they are known as solar granules. Consider them as the uppermost layer of a vast, churning convection cell operating within the sun. The brighter areas within each granule represent superheated fluid at unimaginable temperatures, rising from deep within the sun's upper interior layer towards its surface. Upon reaching this boundary, this incandescent fluid has nowhere left to ascend, and so it spreads outwards and across like a slow-motion celestial wave. As it gradually cools, the fluid then sinks back inwards, descending through the rougher, darker boundaries that encircle each cell before beginning the entire cycle anew. This continuous, dynamic process closely resembles the convection currents that operate within Earth's mantle, which are, in fact, responsible for driving the movement of tectonic plates. This process on the Sun is truly no joke. While, on average, it is estimated that each individual granule lasts for a mere 20 minutes. The furious flow within these cells reaches supersonic speeds, exceeding 7 kilometers per second. This generates powerful waves on the Sun's surface, much like the sonic booms we experience on Earth. Fascinatingly, these granules, though they appear as a grainy texture, can also be discerned in the full, disk view of the Sun we observed earlier, utilizing the same wavelength of visible light. You might have initially thought that image looked somewhat grainy for such a high-tech space probe, and you would be correct. But that graininess is not a processing artifact or excess noise in the image. No, that graininess is, in fact, the solar granules themselves, constantly bubbling and shifting across the Sun's photosphere. And so, sadly, our intimate journey into the Sun's visible layers concludes here. Scientists have not yet devised methods to image deeper into the Sun's interior, using either visible or non-visible light. Much of what lies beyond this outermost layer remains shrouded in profound mystery. However, even with these limitations, we can clearly appreciate the immense benefits of utilizing light across all different spectrums in our ongoing study of the Sun. These diverse wavelengths allow us to observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and endlessly shape-shifting granules, to name just a few, in entirely new and revealing ways. The Sun is, truly, a celestial body buzzing with lively, ceaseless activity, and so much of this dynamic interplay would remain utterly invisible to us, were it not for these advanced imaging techniques. Perhaps, one day, we will uncover novel ways to peer even deeper into its fiery heart, employing techniques that we can barely conceive of currently, just as those ancient generations of humans, long ago, could hardly have dreamed of the sophisticated methods we employ today. But for now, simply knowing that there is so much intricate, unseen activity unfolding within our universe, and understanding that we possess the ingenuity and the tools to uncover it, fills one with a profound sense of excitement and boundless curiosity. Who knows what other astonishing secrets might be awaiting discovery out there in the silent depths of space? If one were to suggest to you, quite calmly, that the very cycles of the Sun could, in fact, subtly affect your entire life, you might, understandably, think that we were suddenly veering away from the realm of astronomy and drifting, gently, into the more speculative domain of astrology. While it is true that many individuals across the globe hold the belief that one can glean insights into their future by studying the precise positions of stars and planets, this is not, typically, the perspective we embrace in these quiet explorations. Our interest lies more profoundly in the sheer, breathtaking beauty of space, and in meticulously understanding the underlying physical mechanisms that explain why the cosmos is the way it is. Yet, sometimes, a kernel of truth, a faint echo of scientific reality, can be found even behind the most surprising and seemingly whimsical of stories. So, for a moment, allow me to playfully don a prophesying hat. While I assure you I am no writer of horoscopes, I will, with a certain confidence, predict that, based on the current state of our Sun, Over the course of the next few years, you might find yourself more susceptible to experiencing subtle shifts in your health, encountering less reliable technology, observing slightly warmer weather patterns with fewer clouds, and perhaps even being influenced in other, surprisingly subtle ways. How, you might ask, could I possibly know this? Because it turns out our magnificent sun, that colossal ball of fire suspended in our sky, is far more than just the singular source of our planet's energy. Emerging scientific evidence is beginning to reveal that its profound, rhythmic 11-year cycles might just be the cosmic metronome subtly measuring out the very rhythm of life on our planet, tick, tick, ticking along. Today, we will gently delve into these fascinating solar cycles. Specifically, I intend to illuminate precisely how the sun's cycles are, even now, subtly influencing the intricate course of your life. It is, of course, no great surprise that the sun exerts an immense influence on life here on Earth. After all, in many fundamental respects, it is the very origin, the primal source, of all life as we know it. Life on Earth, in all its myriad forms, requires a constant input of energy to function, to thrive, to simply exist. And the sun, with unwavering generosity, provides that essential energy. Sunlight nourishes plants, plants sustain herbivores, herbivores feed carnivores, and so on, all the way up the intricate tapestry of the food chain. It is, truly, a challenge to conceive of anything on Earth that could genuinely flourish without the continuous embrace of our sun's life, giving warmth and light. However, beyond this fundamental gift of life, sustaining energy, it is often easy to perceive the sun as a relatively static, unchanging presence. We witness its daily ascent and descent across the sky, a familiar, comforting routine, but we rarely, if ever, notice it undergoing any profound, visible transformation. This, however, is a subtle illusion. The sun in its majestic complexity is, in fact, constantly changing. As scientific understanding has progressively advanced, and as we have developed sophisticated means to shield out the most intense glare of the sun's blinding brilliance, it became possible, as early as 1610, to meticulously study its dynamic surface. From these early observations, it became increasingly clear that the sun was not a static, serene orb, but rather a boiling, shifting, turbulent sea of barely restrained plasma. This plasma, in spite of the immense gravitational force that tirelessly works to hold it all together, frequently escapes its confines, bubbling and bursting on the surface. These spectacular eruptions manifest as solar flares, blazing forth in all directions, sending immense waves of energy across the void. Darker patches, known as sunspots, form drift and then mysteriously vanish across the sun's surface. These sunspots are regions permeated by intense magnetic fields, and they can vary dramatically in size, from a mere 600 kilometers to a colossal 160,000 kilometers across. Furthermore, immense coronal mass ejections, or CMEs, explode outwards from the sun's corona, that ethereal atmospheric zone situated directly above the sun's surface, which curiously is an astonishing 200 times hotter than the surface itself. It is, truly, difficult to find any other region in our vast solar system that exhibits such a continuous, turbulent, and dynamic level of activity as our sun. What many people do not fully realize is that this ceaseless activity, this cosmic dance of light and energy, waxes and wanes. The sun operates on a grand, rhythmic 11-year cycle, alternating between a period of relatively low activity, known as the solar minimum, and a much higher level of intense activity, the solar maximum, before gently returning to the minimum once again. Sunspots, solar flares, and those powerful CMEs all become significantly more common, more frequent, and more intense during the solar maximum. One is, in fact, approximately 50 times more likely to witness a solar flare during a solar maximum period compared to the quieter solar minimum. And large CMEs, which might occur once every few days during the minimum, can erupt multiple times in a single day during the peak of the solar maximum. This grand oscillation is known as the Schwabe cycle. Intriguingly, this 11-year cycle represents just one half of an even larger, more encompassing cycle, known as the Hale cycle. The Hale cycle maps the profound changes in the Sun's magnetic polarity. Every Schwabe cycle, every 11 years, the Sun's magnetic north and south poles gracefully swap places. Then, when another Schwabe cycle completes, the poles swap back again, completing the full 22-year magnetic cycle. This constant, rhythmic rising and falling of solar energy levels, this cosmic pulse, truly thrums through our entire planetary system, rising and falling like a vast, unseen heartbeat. And, surprisingly, even though we cannot directly perceive it, we, here on Earth, move subtly to its ancient rhythm. We don't yet fully comprehend why the Sun undergoes this particular cycle. It is clearly and deeply related to the complex magnetic processes that exist within the Sun itself. Yet, despite having meticulously observed these cycles in action for the past 200 years, and having uncovered compelling evidence of their profound influence on Earth over the last 10,000 years, we remain no closer to definitively figuring out why the Sun's cycle has a length of precisely 11 years, rather than any other duration. What fundamental force, what cosmic choreographer truly drives this majestic, unseen rhythm? Lacking any other obvious, conclusive answer, some scientists have, quite naturally, attempted to connect the orbital period of Jupiter, which is also approximately 11 years, to this solar cycle length. However, this correlation could easily be a mere coincidence. Although Jupiter, in its immense grandeur, represents 2.5 times the combined mass of all the other planets in our solar system and undoubtedly exerts a significant gravitational pull on the Sun, its orbit alone cannot adequately explain the seemingly random variations and subtle complexities that the solar cycle undergoes. Much of what transpires within the Sun's fiery depths remains, to us, a profound mystery. But its pervasive influence on Earth, that, happily, is far easier for us to discern and understand. It begins, quite literally, with the very space that surrounds us. Space, in our increasingly technologically advanced civilization, is becoming more and more indispensable. So, it should come as no surprise that the more frequent occurrence of CMEs and powerful solar storms, streaming outwards from the Sun, would inevitably have a significant impact on the delicate technology we have deployed up there. Scientists, with remarkable precision, are now capable of predicting the arrival of an incoming solar storm, also known as a geomagnetic storm, days, or even weeks, in advance of its impact on Earth. This crucial foresight allows astronauts on the International Space Station, for instance, to retreat into specially shielded safe shelters, protecting themselves from potentially harmful rises in radiation levels. It also enables ground control to power down the delicate hardware on our orbiting satellites, safeguarding them from being fried by the surge of solar radiation. This protective measure is critically important, as solar radiation can induce unexpected electrical currents to form within satellite wiring, potentially overloading and severely damaging systems that have not been placed into a safe standby mode. But there is another, perhaps less expected, aspect to geomagnetic storms that you might not immediately consider. All of that intense radiation also has a subtle, yet significant, impact on our atmosphere itself. It warms it, albeit just a little. As the atmosphere warms, it subtly expands, and this expansion, in turn, has a direct impact on our numerous satellites orbiting in space. In the vacuum of space, it is often said that objects can orbit practically forever, encountering no drag. While this is largely true, satellites in low Earth orbit do, on occasion, typically about 4 times a year, need to expend a small amount of precious fuel to correct their orbits. This is because there is still a minuscule amount of residual atmosphere, even at these altitudes, creating a faint drag. However, when a geomagnetic storm occurs, the atmosphere blossoms upwards, expanding into space. Consequently, low Earth orbit satellites find themselves needing to maneuver much more frequently, every 2 to 3 weeks, to prevent themselves from gradually falling out of orbit due to the sudden increase in atmospheric friction. And sometimes, even these frequent maneuvers are not enough. Consider the powerful geomagnetic storm of 1989. It was so intense, so utterly overwhelming, that it actually knocked NASA's Solar Maximum Mission satellite right out of the sky. The sudden increase in atmospheric density, caused by the storm's warming effect, dramatically slowed the satellite down, causing it to prematurely re-enter Earth's atmosphere. Ironically, this very mission had been dedicated to studying solar flares. This was not an isolated incident. The North American Aerospace Defense Command, or NORAD, routinely has to relocate hundreds of satellites after each significant geomagnetic storm, as they have been subtly nudged out of their established orbits. The influx of solar radiation can also influence our ionosphere, filling it with charged plasma. This, in turn, can have a slight lensing effect on our GPS systems, subtly reducing their accuracy. What might normally pinpoint your location to within a meter could, during such an event, only be accurate to over 10 meters. So, the next time you glance at your navigation app, and it mistakenly places you a street across from your actual location, a geomagnetic storm might just be the quiet culprit. Our crucial power grids, the very backbone of modern society, brace themselves every 11 years for the anticipated uptake in these current-inducing events, striving to prevent themselves from becoming overloaded and collapsing. Amateur radio enthusiasts and airline pilots, relying on high-frequency radio communication, often find their range dropping significantly as radio waves are deflected or even completely blocked by the more powerfully charged ionosphere. As I hinted in my initial horoscope, all of these subtle yet pervasive influences coalesce into a future with, regrettably, some less reliable technology. The fact that the next solar maximum is anticipated to arrive soon, likely in 2025, lends a certain confidence to my gentle prophesying. However, there are, of course, some beautiful bright sides to this increased space weather turbulence. Parts of the world, such as the vast expanses of Canada, witness a remarkable rise in the number of auroras, those ethereal lights dancing hypnotically across the night sky. Aurora chasers, dedicated observers of these celestial phenomena, report increases in sightings from just a few times a year to as many as twice a month during the most energetic periods of the Sun's 11-year cycle. So much for the Sun's profound influence on the realm of space and our delicate technology. You might, at this point, reasonably conclude that that's the extent of it. The solar cycle might influence machinery, but it's surely not going to make much of a difference to anything truly alive, right? Right? If you hold that thought, you would, in fact, be mistaken. It is not without reason that the rest of my initial horoscope gently alluded to the possibility of poorer health. There is a growing body of evidence suggesting that the sun's cycles can, indeed, subtly influence entire ecosystems and even species themselves, including, remarkably, humans. Some of this influence is incidental, a delicate chain of indirect effects. For instance, when the Schwabe cycle is at its solar minimum, the sun exerts less pressure through its solar winds. This, somewhat ironically, means that we receive slightly less protection from our heliosphere against the constant barrage of cosmic radiation. This form of radiation, while highly energetic, fortunately rarely penetrates our atmosphere to reach the surface directly. This is precisely because it is highly likely to be absorbed or deflected by a passing air molecule. However, merely reaching the atmosphere is all that is needed to produce a subtle effect. There is a theory, though it remains far from certain, that this extra influx of cosmic radiation could be creating tiny nucleation sites in the atmosphere, which, in turn, might seed the formation of extra clouds, thereby subtly influencing our weather patterns. Even if this specific mechanism is not precisely occurring during a solar maximum, the heightened space weather impacting our atmosphere can indeed raise global temperatures slightly, as my initial predictions suggested, leading to a gentle warming of the weather. Not by much, it should be said, less than half a degree Celsius, and the temperature always, eventually, returns to its baseline. But it is a subtle shift, enough to be noticeable to species that are acutely attuned to temperature, for instance, when deciding precisely when to commence their mating season. Studies of various bird species, for example, have consistently shown that in warmer years, they tend to lay their eggs earlier in the season. Curiously, a study published in 2009 by researchers in the Netherlands even went as far as to demonstrate that the laying times of blue tits were also subtly affected by the fluctuating number of sunspots. Even the researchers themselves found this connection challenging to explain, as it's not as if birds possess the capability to observe the sun and count its sunspots. Nevertheless, a subtle, yet discernible, link appears to exist, according to the 5 distinct nesting groups that were meticulously observed. This subtle influence is not something that affects only blue tits, or even species like homing pigeons, which are known to be particularly sensitive to magnetic fluctuations, and which are observed to fly different routes depending on where the 11-year solar cycle currently stands. No, I am referring to that last, unmentioned point in my earlier horoscope, subtle shifts in health. There are numerous ongoing studies exploring how solar cycles might subtly influence this aspect of human experience. In 2011, a comprehensive study spanning 2 decades, involving nearly 1/3 of all women in Holland, uncovered a subtle peak in 6 distinct cervical pathologies that consistently occurred just after a solar maximum, when the sun's radiation was at its most intense. The study also, admittedly, checked only 1 man during the same period, which is, of course, a much smaller number of candidates. Still, it was interesting to note that this individual experienced slight, yet measurable, elevations in oral temperature, pulse rate, blood pressure, and respiration rate, which also consistently took place soon after a solar maximum. The influence isn't solely physical. There's even evidence of a subtle impact on the rate of mental disorders. A study conducted in 2006 meticulously examined 237,000 clients within the main Medicaid database, with data collected between 1995 and 2004. They made a fascinating discovery. Among all those clients, those born during higher energy, more chaotic solar cycles experienced a subtly increased rate of certain mental disorders. If this intriguing correlation proves to be robust, then the subtle rhythm of the sun's cycle at the precise moment of your birth might just have, in some minor way, influenced the subsequent course of your life. It's not quite the star signs of traditional astrology, but perhaps, just perhaps, astrology might be onto something, at least with one very specific, very powerful star. Ultimately, the scientific investigation into these connections is still very much ongoing, and it must be gently stressed that any health impacts potentially caused by these solar cycles are, at present, considered extremely minor. As one researcher succinctly put it, it took hundreds of thousands of patient records to even begin to notice that a subtle health impact existed. The sun's cycle, therefore, should certainly not prevent you from living your life with joy and purpose. We are currently, as it happens, heading towards a solar maximum, predicted to arrive sometime in 2025. But for those who might feel a flicker of concern, living through, or even being born during, a solar maximum isn't entirely without its positive aspects. The same comprehensive study subtly suggested that this increased radiation might, paradoxically, lead to a gentle rise in creativity and adaptability within the human population. Perhaps it was during one such powerful solar maximum, some 80,000 years ago, that a crucial mutation occurred within a developing human brain, bestowing upon it the incredible gifts of abstract thought and profound consciousness. If that is indeed the case, if these energetic bursts from our sun provided us with the very means to perceive, to question, to understand the universe around us, then we truly have a great deal to thank solar maximums for. We wouldn't, quite simply, be without them. What does the sun truly sound like? It is, on the surface, a simple enough question, and one that, at first glance, comes with an equally simple, almost self-evident answer: the sun is silent, of course. This is because sound, as we understand it, requires a medium through which to travel, and the vast expanse of space between us and our star is, by its very nature, a near, perfect vacuum. To us, observing from Earth, the sun sounds like nothing at all. But let us, for a moment, gently set aside these simple answers. What if, in a delightful thought experiment, sound could, in fact, propagate through space without the need for a giant, cosmic muffler dampening its every vibration? What, then, would we hear? Would the sun serenade us with an enchanting, celestial melody, a gentle hum in our sky? Or would its raw, unbridled noise be such a cataclysmic cacophony that it would instantly become the last thing our ears ever registered? Remarkably, scientists actually possess an answer to this intriguing question. Through the ingenious work of spacecraft like the Parker Solar Probe, which is currently undertaking daring, skimming orbits around the sun, they are able to detect the subtle pressure waves and energetic particles constantly emitted by our star. These waves and particles can then be meticulously converted into the sounds we might perceive if space were indeed capable of propagating such vibrations. And, intriguingly enough, not all of the sun's sounds are precisely the same. Join with me today as we listen to several distinct sounds made by the sun, meticulously recreated through the elegance of clever science. For it turns out, these very sounds may eventually allow scientists to unravel two of the sun's most profound and enduring mysteries. In our imaginary scenario, where the vacuum of space has, quite suddenly, acquired the miraculous ability to propagate sound, we can now begin our auditory journey, listening to the sun all the way from Earth. Although our planet is on average a formidable 152 million kilometers away from the sun, it is, perhaps, unsurprising to learn that even at this vast distance, the sun would be incredibly loud, easily audible from where we stand. It would, in this imagined reality, sound something like this: a sound of low, powerful, continuous hum, like a distant, immense generator. Just a gentle reminder, of course, there is no actual sound in space. This is a meticulous sound reconstruction, a scientific translation, converting the amplitudes and frequencies of detected waves into audible sound waves, crafting clips of what those waves might sound like to the human ear, if a medium, an atmosphere, were miraculously present. This soothing, yet undeniably powerful, buzz possesses an almost electrical quality. It evokes the sensation of colossal generators humming, or perhaps even something vaguely radioactive, which, given that we are discussing the sun, is entirely appropriate. The ceaseless nuclear fusion occurring deep within the sun's core generates an astounding 3.85 x 1026 watts of energy every single second. To put that into perspective, it's roughly 1,000,000 times more energy than all of humanity collectively produces in an entire year. All of this immense power, being constantly created, has an unsurprising, dramatic knock-on effect on the sheer volume of the sound the sun would produce. To truly grasp the magnitude of this imagined volume, consider this: take the device you are currently using to experience this, and imagine it connected to the colossal speakers used at your next rock concert. Then, Play this recreated noise at its absolute full blast. At an astounding 110 decibels, this volume level is, in principle, survivable for short, very limited periods of time. However, if it were to play incessantly in our sky, non-stop, it would almost certainly result in the entire population of our planet suffering permanent hearing loss, unless they were diligently wearing robust earplugs at all times. In fact, we can consider ourselves incredibly fortunate that we do not, in reality, have to contend with this constant sonic assault. Our species would have, in all likelihood, evolved without the faculty of hearing at all, as such an ability would be utterly pointless in a world dominated by such an overwhelming, continuous roar. As we imagine ourselves drawing closer to the fiery surface of the sun, that sound level, unfathomably, grows exponentially. Some experts estimate it would reach an astonishing 270 decibels. Remember, the decibel scale is logarithmic, meaning that for every 10 decibel increase, the sound level is multiplied by a factor of 10. To truly grasp the immensity of this, 270 decibels is a volume so extreme that our very atmosphere, the air around us, cannot physically convey it. There is a theoretical cap on sound in Earth's atmosphere, typically around 190 decibels, as different mediums possess different volume caps due to complex quirks of wave amplitude and energy levels, which we won't delve into here. The volume of the sun at its surface would be a staggering 100 million times higher than this atmospheric cap. The sun is unequivocally loud, which is perhaps a shame, as some of the sun's more intricate sounds, its subtle nuances, can only be differentiated when we enter that ear-splitting, mind-numbingly loud zone. By the time the overwhelming noise of the sun has traversed the vast distance to reach us on Earth, many of its distinct sounds have blurred, coalescing into one undifferentiated hum, meaning we miss out on some of their most fascinating intricacies. To gain a truly better insight into the sun's complex auditory landscape, we would need to get much, much closer, venturing directly into that blisteringly loud, deafening zone of noise. So, for the purpose of our tranquil exploration, let us, for now, gently set aside the sheer, overwhelming volume of the sun, and instead, focus our attention on its subtle, underlying sound patterns. If we were to embark on an imaginary journey aboard a spacecraft, quietly heading towards the sun, we would soon begin to perceive a distinct difference in the sound's uniformity. Rather than a constant, unvarying buzzing, we would start to hear something more akin to this sound of a rushing, hissing, slightly variable wind, with faint underlying hum. This, my friends, is the sound of the solar wind. The sun, ceaselessly, emits a constant, energetic stream of charged particles that blasts outwards across the entire solar system. The very existence of this solar wind represents one of the sun's greatest and most enduring enigmas to date. You see, it is tempting, quite naturally, to conceive of this stream as originating deep inside the sun, blasting outwards under the incredible, relentless force of all that nuclear fusion. However, by the 1960s, a crucial, unexpected discovery had been made through meticulous observation. While particles within the sun's atmosphere, its corona, were observed to be moving around with an average speed of approximately 145 meters per second, particles outside of the corona were detected traveling at a far greater velocity, 618 meters per second. This significant discrepancy meant something profound. Particles that possessed just enough speed to initially escape from the sun's surface were merely drifting into space. But then, mysteriously, something within the sun's corona was accelerating them, propelling them from subsonic to supersonic speeds, effectively firing them off into the cosmos. What kind of powerful process, what unknown mechanism, is orchestrating this incredible acceleration? This question, to this very day, remains a profound mystery. The corona, that luminous crown, harbors a second, equally perplexing enigma. It is far, far too hot. While one might logically expect the very center of the sun, its core, to be its warmest part, and for the temperature to gradually, predictably, decrease the further one travels from that fiery heart. This logical progression dramatically ceases to be true once you enter the corona. The visible surface of the sun, the photosphere, has an average temperature of approximately 500–600 degrees Celsius. But within a mere few thousand kilometers, the corona abruptly sees its temperature skyrocket, jumping to an astonishing 2 million degrees Celsius, sometimes even higher. Something, quite clearly, within the sun's corona is both violently flicking solar wind into space and simultaneously making everything incredibly hot. Scientists, as yet, do not definitively know why this is happening, although it is widely thought to have something fundamental to do with the sun's powerful and complex magnetic fields. It is here, at this boundary, that we would encounter the third distinct sound of our auditory tour of the sun. As our imaginary spaceship would draw ever closer, and we gently passed over the critical boundary between the corona and the vast emptiness of space, a boundary known to scientists as the Alfvén surface, we would begin to perceive the following: our sound of delicate, high-pitched chirps and whistles like a boiling kettle, but on a cosmic scale, interwoven with the rushing wind. These are known as L-mode waves, or sometimes more simply, Whistler waves. They are formed by tiny, intricate oscillations of plasma particles, vibrated by the sheer force of light itself. As these particles stream outwards from the sun through countless tiny funnel-like structures on its surface. It's a magnetic equivalent, perhaps, to the familiar sound a kettle makes when it boils, but on a scale that defies easy comprehension. We would, in our journey, have entered one such stream. Countless these energetic streams fire out from the sun's surface, a continuous barrage. The sun's exterior is, in fact, covered in innumerable islands of superheated material, constantly rising from the star's fiery center. Once these materials reach the surface, they cool, gradually, and then sink back inwards, descending into the star's immense mass along the edges of these islands. And something profound about this relentless process of rising and falling material, or perhaps something deeper, occurring within the sun itself, causes these sinking zones to stream out powerful, intricate magnetic field lines. Plasma is then scooped up by this immense magnetic force and is sent streaming into space, marking the very starting point of the solar wind. Scientists still do not fully comprehend what causes this specific process, but the sound of these L-mode waves, these delicate chirps and whistles, is undeniably, eerily beautiful. As these solar winds journey outwards, not all of the waves created in this way travel at the exact same speed. This fundamental difference in velocity has the effect of subtly spreading out the sounds, as faster parts of the wave push ahead, while slower parts of the wave lag behind, creating what are known as dispersive waves. Such waves are filled with subtle, chorus elements, little eddies of sound where faster waves, approaching from behind, eventually meet slower waves already traveling ahead. Eventually, this intricate pattern evens out, dissipating into the more uniform, continuous hum we initially heard at the beginning of our auditory journey. There is, however, one last, crucial sound that might offer a profound insight into this entire cosmic mystery, one that carries some truly intriguing implications. Here, deep within the sun's boiling corona, we can finally begin to detect what are known as Whistler mode waves. Whistler waves are, in essence, the distant, lingering echoes of high-energy events that reverberate through the plasma of a celestial body's magnetosphere. We experience them here on Earth whenever lightning dramatically cracks across the sky. You get more than just the familiar rumble of thunder. A distinct ripple travels through our planet's magnetosphere, a ripple that can be picked up many kilometers away, if one possesses the right sensitive detectors. To truly grasp the scale of these waves, consider what they sound like on Earth, just a few small, isolated cracks and whistles, nothing too extraordinary. Now, compare that to what they sound like on the Sun. Sound shifts to a continuous, roaring, wailing torrent of crackles, whistles, and intense static, overwhelming and incessant, to transition from sparse, brief clicks to a veritable cacophony of wailing, tempestuous wind indicates, unequivocally, that the Sun's magnetosphere is not merely experiencing the occasional crack of lightning. Something is occurring constantly, relentlessly, all over its vast expanse, merging individual, powerful moments together into one incessant, overwhelming roar. Scientists are still diligently striving to decipher precisely what is causing that continuous, deafening roar. But at least one prominent theory for the powerful force behind this sound. A theory that can account for both the dramatic acceleration and the extreme superheating of matter within the corona, is a rather dry-sounding, technical event called magnetic reconnection. Magnetic reconnection, despite its fairly innocuous and technical-sounding name, in fact disguises a cosmic cataclysm. The Sun is, fundamentally, a tensely wound-up, immensely powerful ball of constantly shifting magnetic field lines, all due to that turbulent, churning plasma deep within its fiery heart. One cannot stress enough the sheer power embedded within these magnetic fields. When magnetic field lines travel away from the Sun, it is sometimes possible for them to merge with other field lines, causing some of those iconic, graceful loops to form that you have likely seen in countless images of the Sun. However, at the precise moment such arcs are formed, all cosmic hell breaks loose. When two parallel magnetic field lines, under immense tension, suddenly touch and reconnect. To create an arc, there is a massive, instantaneous realignment in the polarity of the excess field lines. Everything above the newly formed arc needs to find a new place to go to ensure that magnetic equilibrium is swiftly maintained. Cut from their original tethers, the field lines further out from the Sun quickly form an arc of their own, which then catapults off into space, much like the sudden, violent releasing of a gargantuan, impossibly stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees Celsius in mere seconds. Scientists have only very recently developed the technological capability to even see nanoflares, and they are not yet entirely certain that the nanoflares they have observed are, indeed, the hypothesized events they were expecting. Although these observed events seem to be accompanied by the expected, dramatic superheating. This entire explanation, this intricate dance of magnetic reconnection, is still very much a work in progress, a theory being meticulously refined. Much of its complex mechanics is not yet fully understood. And yet, it is not entirely far-fetched to suggest that such moments, when the Sun's immense magnetic fields become so wound up that they violently snap, could explain why its corona is as astonishingly hot as it is, and why it is continuously flinging solar winds out across the solar system with such incredible force. Although, to transition from a single, isolated crack into the roaring, incessant wail that we hear, and to account for the constant, pervasive solar wind traveling outwards in all directions from the Sun, nanoflares, or whatever the underlying force behind this phenomenon truly is, must be incredibly widespread, occurring almost constantly throughout the entire corona. The Sun, in its magnificent complexity, continues to hold many profound mysteries. The Parker Solar Probe, which has diligently collected much of the data used to reconstruct these sounds, continues its daring journey around the Sun, gathering invaluable information with every close pass. The Parker Probe is, remarkably, only 4 years into its ambitious 7-year mission, so hopefully, it will collect a great deal more crucial information for scientists to pore over, to meticulously analyze. Perhaps they will even discover more sounds for us, each one a subtle, invaluable clue to the ancient, enduring riddle of how the universe truly works. For, ironically, just like listening to the intricate ticking of a clock to try and decipher the workings of its internal mechanism, the deepest secrets of the sun might, one day, be solved not by what we visually observe, but by what we quietly, meticulously hear. There is something deeply ingrained, something almost hardwired, into the very essence of humanity, the profound desire to be remembered. For thousands upon thousands of years of humankind's long and winding history, people have, with great effort and often immense resources, erected colossal monuments to themselves or performed deeds of extraordinary grandeur, all with the singular aim of enduring, of leaving an indelible mark long after their own passing. It is, therefore, no wonder that some individuals might aspire to be the one who makes a truly monumental scientific discovery, perhaps unearthing a previously unknown star or a hidden planet, thus ensuring their name would resonate through the annals of time. However, such an overzealous pursuit of recognition could, paradoxically, lead to being remembered for all the wrong reasons. Today, we will gently delve into the fascinating, almost mythical, discovery of a planet that was believed to reside within our own solar system, even closer to the Sun than Mercury itself. It was reportedly observed dozens of times by various esteemed astronomers. The only problem, the subtle, yet crucial, detail it doesn't actually exist. Let us, for a moment, rewind the grand clock of history back to the year 1846. Something truly astounding had just captivated the scientific community. Urbain Jean-Joseph Leverrier, a brilliant French astronomer and mathematician, had, through sheer intellectual prowess, helped to discover the planet Neptune, using nothing more than the elegant power of pure mathematics. He had been meticulously examining the observed rotation of the then-known 7 planets when he noticed a subtle, yet persistent, anomaly in the orbit of Uranus. It simply did not seem to be moving precisely in line with the established theories of gravity, as proposed by the venerable Newtonian physics. Leverrier, with unwavering confidence, reasoned that the only logical explanation for this subtle discrepancy was the undeniable presence of an as-yet undiscovered planet, situated beyond the orbit of Uranus, whose gravitational influence was subtly perturbing its motion. To account for this intricate deviation, he performed a series of complex mathematical calculations and then, with remarkable precision, declared that this 8th planet must exist at an exact, predetermined point in the night sky. The truly incredible aspect of this tale, that upon hearing his bold prediction, Leverrier's friend, Johann Gottfried Geil, an astronomer at the Berlin Observatory, promptly retrieved a telescope, pointed it to the precise location indicated, and, sure enough, discovered the planet Neptune in a single, astonishing hour. It was almost exactly where Leverrier had predicted it would be. The scientific community, understandably, erupted with excitement over this monumental discovery, and Leverrier was, quite rightly, celebrated far and wide for his incredible, almost prophetic deductions. So, it is hardly surprising that a mere decade later, when he again predicted the location of a 9th planet, employing the very same, highly successful methodology, the scientific community listened with rapt attention and considerable anticipation. In fairness, Leverrier had not been the first to speculate about the existence of such a planet. As far back as 1601, the German astronomer Christoph Scheiner had claimed to have noticed a strange, dark spot moving slowly in front of the Sun and had confidently declared this to be a planet. In reality, it was most probably nothing more than a prominent sunspot. Other alleged sightings had been made throughout the ensuing years. A Kappa loft in 1818, a Franz von Gruithuisen in 1819, and J.W. Pastorff between 1822 and 1837, all claim to have observed an object, or indeed multiple objects, orbiting the Sun. Pastorff, in particular, claimed to have seen it on at least 12 different occasions. People had even begun to playfully spitball potential names for this hypothetical planet. In 1846, the French astronomer Jacques Babinet suggested calling it Vulcan, after the Roman god of volcanoes, fire, and metalwork. This would, indeed, have been an entirely appropriate name, as any planet situated closer to the Sun than Mercury would have been exceptionally, impossibly hot. Mercury itself already experiences surface temperatures reaching a scorching 427 degrees Celsius. Vulcan would have been an even more infernal realm. And yet, for all these tantalizing sightings, definitive, repeatable confirmation of the planet remained stubbornly elusive. But what truly elevated Leverrier's claims above all previous speculation was the rigorous, mathematical approach he had employed to arrive at his prediction. In 1845, even before his celebrated discovery of Neptune, Leverrier had been tasked by the esteemed director of the Paris Observatory to apply Newton's fundamental laws of physics to the observed orbit of the planet Mercury, to ascertain if the theoretical and observed paths perfectly aligned. Leverrier diligently undertook this task, meticulously laying out a theoretical orbit that Mercury should follow around the Sun, based purely on the principles of Newtonian physics. Once his intricate prediction was complete, astronomers then carefully observed Mercury to see how well its actual path matched Leverrier's theoretical calculations. Only, to their surprise, it did not. The discrepancy, though slight, was undeniable. Leverrier, a man of profound intellectual rigor, tried again, reasoning that it was possible his initial mathematics might have contained some subtle error. He embarked on a much more thorough and exhaustive study in 1859, incorporating multiple observed sightings of Mercury as his baseline data. He once again painstakingly mapped out Mercury's theoretical orbit. But once again, his meticulous predictions were slightly, stubbornly off. Not by a vast amount, merely 45 arcseconds per century, but enough, critically, that there was conclusively something unusual, something anomalous, occurring. Confident in the absolute precision of his mathematics this time, Leverrier reached the profound conclusion that there must be some additional, unseen mass whose gravitational pull was subtly tugging Mercury out from its idealized Newtonian orbit. This unseen mass, he reasoned, could either be another planet or perhaps a series of smaller asteroids. Given his recent, spectacular success in precisely locating Neptune, many astronomers readily believed him. Scientists, eager for another grand discovery, rushed to their telescopes, straining to spot this alleged new planet. And it was not long before reports, tantalizingly, began to trickle in. Spotting a planet so incredibly close to the Sun was, by its very nature, an inherently difficult endeavor. The blinding glare of the Sun would utterly obliterate the faint, reflected shine of a tiny, distant planet. As such, the most effective, indeed almost the only, method of spotting such an object was to observe the subtle darkening it caused as it transited, or passed, directly across the Sun's fiery disk. And in 1859, a certain Edmond Modeste Lescarbault, a French amateur astronomer and physician, claimed to have seen precisely that. Using relatively basic tools in his homemade observatory, Lescarbault confidently asserted that he had spotted a small, dark object passing majestically across the Sun on the 22nd of December. He promptly wrote to Leverrier, who was so profoundly intrigued by this claim that he traveled, unannounced, by train, to Lescarbault's remote home, seeking to personally verify the observation. He questioned Lescarbault meticulously, listened intently to his observations, and ultimately came to the powerful conclusion that the man was, indeed, telling the truth. And so, with a shared sense of triumph, The two of them announced Lescarbault's momentous discovery to the eager scientific community. They, of course, named the planet Vulcan. The scientific community was, once again, deeply impressed. Lescarbault himself was awarded the Légion d'honneur, the highest order of merit in France, and was invited to speak at prestigious meetings of learned scholars. There was, however, just one crucial problem. The planet he had so confidently discovered didn't actually exist. There were numerous, increasingly compelling proofs of this unfortunate reality. For one, naturally, other scientists, fueled by both curiosity and a desire for independent verification, yearned to take a look at this exciting new planet, Vulcan. Leverrier, using Lescarbault's observations as his guide, calculated that Vulcans must orbit approximately 21 million kilometers out from the Sun, completing a full revolution every 19 days and 17 hours. This meant, theoretically, it should be relatively easy to spot, as its subsequent transits across the Sun would be precisely calculable. Astronomers, with bated breath, pointed their powerful telescopes towards the Sun at the appointed times, but alas, Vulcan was a persistent no-show. Leverrier was troubled by this frustrating absence, but by then, more reports of the planet's sighting were continuing to trickle in. Other astronomers, going back through their dusty records, began to match up various phenomena they had previously observed with this new planet, Vulcan. Some of these alleged sightings were years out of date, and not even clearly listed as to when in the year they had occurred. Yet, Leverrier, clinging to his theory, still used these nebulous reports to subtly tinker with his mathematical model, reasoning that perhaps his initial calculations were just slightly off. And so, he would predict, and would not see Vulcan, and would then rework his theory, and would not see it again. Another piece of increasingly damning proof emerged from Emmanuel Liais, another French astronomer. Liais claimed that he had, by a remarkable coincidence, been looking directly at the Sun at the exact moment Lescarbault had, using a telescope twice as powerful, and he had seen absolutely no trace of the planet Lescarbault had so confidently claimed to observe. Despite these growing doubts, Vulcan's existence continued to float through murky scientific waters, as several renowned scientists did claim to glimpse it from time to time. Leverrier, the great predictor, passed away in 1877, but just a year later in 1878. Two other well-respected astronomers both claimed to have seen Vulcan at the same point in the sky, at the same time, during a total solar eclipse. They even both asserted that the planet possessed a distinct reddish hue. This collaboration of sightings was, at the time, compelling. Yet, despite these fervent claims, Vulcan still did not exist. In science, a fundamental principle dictates that if a fact is true, then it must be repeatable, verifiable by independent observers. And in spite of all these reported observations throughout the years, Vulcan was never repeatedly, consistently observed. It was never seen during a solar eclipse again by multiple, independent witnesses. In time, that seemingly corroborated 1878 sighting was eventually attributed to subtle calculation errors and the misidentification of a known star. But ultimately, the individual who finally, definitively, laid the idea of Vulcan to rest was none other than Albert Einstein. And he did so quite brilliantly. By thinking about something completely different. Numerous scientists, over many decades, had diligently attempted to visually confirm Leverrier's hypothetical planet, Vulcan, because, mathematically, they were absolutely certain it had to exist. Newtonian physics, the bedrock of their understanding, demanded its presence. They strained their eyes to see it, and in that powerful confirmation bias, they did see it, again and again, just never consistently in the same place. But Einstein, with his revolutionary insight, realized that it was, in fact, Newtonian physics itself that was at fault. In 1915, he proposed a radical new model of physics. his theory of general relativity, which accurately described the motion of the universe, but relied on entirely new concepts, such as the curvature of spacetime, rather than the simpler notion of gravity as a direct force. At slow speeds, and for objects far from massive bodies, Einstein's theory looked remarkably similar to Newtonian physics. But when you placed objects like Mercury next to very massive objects, such as the Sun, special relativity predicted a subtly, yet significantly, different path for their orbits. And sure enough, Einstein's elegant model precisely predicted the exact orbit that Mercury made around the Sun, deviations and all. And with that profound breakthrough, the case for Vulcan's existence simply evaporated. Under the framework of special relativity, it couldn't exist. There could be no object of planetary size so close to the Sun, or it would profoundly interfere with Mercury's orbit in a way that would no longer align with Einstein's new, accurate mathematics. And this time, Einstein was able to prove his mathematics correct through rigorous observational tests, such as the famous Eddington experiment during a solar eclipse. There is a profound lesson embedded within this tale, isn't there? Sometimes, if we desire something too intensely, if we are too wedded to a preconceived notion, we may find it regardless of whether it is truly there or not. Sometimes, it takes the courage to think entirely outside the established box, to challenge our most deeply held beliefs before the actual truth can finally be uncovered. As scientists, and equally, as everyday individuals, it is crucial that we do not cling too tightly to our cherished ideas. The truth, in its immutable nature, does not require our fervent belief. It will, given sufficient time and ample opportunities for repeatable verification, ultimately prove itself. So there you have it, the planet Vulcan, a planet of fire that was, in reality, nothing but smoke and mirrors. A yearning for something that simply never materialized into reality. Newtonian physics, for all its former glory, was eventually replaced by Einstein's groundbreaking theories of relativity. And now, special relativity is here to stay, at least until it is, in turn, supplanted by something even more comprehensive and profound. Have you ever gazed up at the sky and witnessed something so utterly strange, so unexpectedly beautiful, that it momentarily made you question if you were, perhaps, dreaming? Perhaps you saw what appeared to be a rainbow, only it was dramatically inverted, an upside-down arc of color. Or maybe you observed a perfect, luminous circle of light encircling the Sun, flanked by two vivid splashes of rainbow color on its sides. Well, there's no need to pinch yourself, for what you were witnessing was not a dream, but a unique and captivating category of optical phenomena called ice halos. While visually similar to rainbows, they are not, technically speaking, rainbows themselves. They are their own distinct wonder, born of different atmospheric conditions. Some ice halos are relatively common, gracing our skies with moderate frequency, while others are exquisitely rare, appearing only under precise and fleeting circumstances. As you may already know, rainbows occur when sunlight is refracted by countless tiny water droplets suspended in the atmosphere. When light, that incredible traveler, passes from one transparent substance into another, such as from the diffuse air into a denser water droplet, its speed subtly changes. This change in speed causes its path to bend or refract, and simultaneously, it separates the white light into its constituent colored bands, each defined by its unique wavelength. This beautiful process is known as dispersion. But what, then, happens when light encounters water particles that are frozen, transformed into ice crystals, rather than remaining in their liquid water state? Well, depending on the precise shape and orientation of these ice crystals, as well as the exact direction from which the light strikes them, they can produce an astonishing array of optical phenomena. To date, a remarkable 119 distinct kinds of ice halos have been meticulously categorized And it is entirely possible that even more, as yet undiscovered, varieties still await our patient observation. So, what exactly are ice halos? How do these ethereal spectacles form? And what specific visual cues should you look for if you wish to witness one for yourself? And finally, is there, perhaps, a deeper, more ominous significance to their appearance on the horizon? Join me today as we serenely contemplate spectacular images of some of the better-known ice halos and gently uncover the underlying physics of how and why these delicately beautiful spectacles materialize in our skies. This stunning photograph, for instance, showcases a magnificent 22-degree solar halo spotted gracefully suspended over Gurkau, Germany. The 22 degrees here does not, as one might first assume, refer to temperature. Rather, it denotes the angular radius of the halo. To visualize this, imagine drawing a direct, straight line from a single point on the halo's luminous ring to the observer's eye. Then, perform the same mental exercise, drawing a line from the very center of the sun, which is the center of the halo's circle, to the observer's eye. The angle formed between these two imaginary sight lines is precisely 22 degrees, hence its descriptive name, the 22-degree halo. There are also 46-degree halos, which, as you might correctly guess, are significantly larger than their 22-degree cousins, but are also, typically, much fainter and more elusive. Halos can also, quite beautifully, occur in moonlight, as you can observe in this serene image. These eerily beautiful, luminous rings are known as moon rings or sometimes winter halos. They are, however, technically the very same optical phenomenon as solar halos. What distinguishes them is simply the source of the light that creates them. In some images, you might notice that the patch of sky inside a halo appears distinctly darker than the sky outside the luminous ring. This creates a dramatic visual effect, sometimes evocatively described as a hole in the sky. This intriguing phenomenon occurs because when light interacts, bouncing and refracting off the myriad ice crystals, none of it is reflected directly back towards the light source. To an observer, this absence of directly reflected light leads to an apparent, and quite striking, darkening within the halo's embrace. But this, truly, is just the tip of the iceberg. Ice halos, in their full glory, can assume all kinds of strange and shocking forms, vivid spots of concentrated color, those previously mentioned upside-down rainbows, and even, quite astonishingly, upside-down rainbows appearing at night. But before we delve further into these wonders, let us take a tranquil moment to break down the fascinating optics that meticulously produce these strange and captivating occurrences. Most circular halos, those ethereal rings, are formed by countless tiny water crystals suspended within cirrus or cirrostratus clouds. These delicate, wispy clouds typically form high in the troposphere, usually at altitudes ranging from 5 to 10 kilometers above the Earth's surface, where temperatures are consistently very cold. As a direct result of these high-altitude conditions, halos can, remarkably, be observed anywhere on Earth, all year long, even in intensely hot climates. Atmospheric ice crystals are, individually, incredibly small, usually less than 10 micrometers long, and they are remarkably uniform in both size and shape. This extreme regularity, this precise crystalline order, is fundamentally linked to the intricate structure of ice at a molecular level, and it is absolutely essential for the formation of distinct, visible halos. You see, water molecules consist of two hydrogen atoms bonded to a single oxygen atom. In liquid water, the bonds between these hydrogen atoms are weak and transient. They are constantly breaking and reforming as the molecules slip and slide past each other in a fluid dance. But when water freezes, that frenetic molecular movement slows dramatically, eventually coming to a halt, and the bonds between hydrogen atoms become fixed, locked into place. This results in a highly organized, repeating hexagonal lattice structure, often referred to as a tetrahedral arrangement. This highly organized structure, evident at the molecular scale, is precisely what causes the individual ice particles to form hexagonal crystals. Some of these crystals are flat, resembling tiny plates, while others appear as elongated columns with a hexagonal cross-section. Despite this subtle variation in macroscopic shape, these crystals behave with remarkable uniformity because of their immutable interfacial angles. In fact, the angles between any two faces of ice crystals are, fundamentally, completely identical. It is this extreme regularity of these interfacial angles, rather than the crystal's overall mass or precise shape, that allows millions upon millions of these tiny particles to scatter the light, with the extraordinary consistency required to produce a visible, coherent halo. Halos are, sometimes, quite beautifully colorful. This is because when these ice crystals refract light, the red and blue frequencies, the different wavelengths, bend at slightly different angles and disperse, much like in a rainbow. Some 22-degree halos, for example, exhibit two distinct, vibrant spots of color, visible to the left and right of the sun. These beautiful, luminous phenomena are called perhelia, or more commonly, sundogs. Sundogs appear when ice crystals, which are specifically shaped like hexagonal plates, adopt a horizontal orientation as they drift through the atmosphere. As I mentioned earlier, some crystals form as thin hexagonal plates, while others develop as columns with hexagonal cross-sections. When these plate-shaped crystals form and then slowly settle downwards, atmospheric drag naturally orients them horizontally, with their C-axis, the longest axis of the hexagon, positioned almost perfectly perpendicular to the ground. Larger plates tend to wobble just a little bit more than smaller ones as they fall. This subtle wobble, in turn, directly affects how tall or vertically stretched the sundogs appear to be, with wobblier plates causing the sundogs to appear more elongated. Sundogs are sometimes accompanied by another captivating optical phenomenon called a circumzenithal arc. These arcs, visually, bear a striking resemblance to rainbows, but with one key difference: they are dramatically upside down, which often gives them a friendly, almost smiling appearance in the sky. These unusual arcs appear directly over the sun, but only when the direction of the sunlight and the precise orientation of the ice crystals are just right. This specific phenomenon occurs when light enters the top faces of hexagonal plate crystals and then exits through their side faces. However, this precise interaction can only happen when the sun is lower than 32.2 degrees above the horizon and also more than 5 degrees above it. Because these ice crystals function, in essence, like miniature 90-degree prisms, the resulting color separation is exceptionally good. This means that circumzenithal arcs exhibit a far higher clarity and purity of color than actual rainbows. And if you are truly fortunate, truly lucky, you might even spot one accompanied by moon rings, a combination known as a lunar circumzenithal arc. These unusual, ghostly arcs only appear when the moon is exceptionally bright and positioned fairly low on the horizon. As strange as it sounds, it is indeed possible to witness what appears to be an upside-down rainbow shimmering softly in the night sky. Now, this is truly amazing. Circular halos have also been sighted on Mars. Here, for instance, is a remarkable image taken by the Perseverance rover on the 15th of December, 2021. This unexpected discovery has led some scientists to suggest that the cause may be the presence of carbon dioxide crystals within the planet's incredibly cold, thin atmosphere, or perhaps a complex mixture of CO2 and water ice. We didn't always know that halos occurred on Mars, so as you can well imagine, the Perseverance team was profoundly excited by this visual confirmation, because the precise size and appearance of these Martian halos provide crucial clues about the specific types of crystals forming in that alien atmosphere. Scientists hope that by diligently studying halos here on Earth, and by actively spotting them on other planets and moons, they can shed new light on the atmospheric composition of those distant worlds. As a result, more dedicated research will undoubtedly be undertaken in the future to meticulously document and understand the delicate appearance of ice halos on Mars, as well as on other fascinating moons and planets throughout our solar system. So there you have it, a gentle primer on some of the more well-known ice halos and their associated optical phenomena. And if you, yourself, wish to witness one of these ethereal displays, here are a few quiet things to look for. First, always check for the presence of cirrus clouds. These are the high-altitude, wispy clouds that contain the tiny ice particles absolutely necessary to produce ice halos. Second, keep a gentle eye on the sun or moon, but always take care not to stare directly at the sun, as this can cause irreversible damage to your eyes. While rainbows typically form around the anti-solar point, which is located directly opposite the sun in the celestial dome, most ice halos form in close proximity to the sun or moon itself. And while ice halos tend to appear during fair weather, they often, intriguingly, precede the front of an approaching storm system. This means that if you happen to see one, it might be a gentle hint not to linger outside for too long. Perhaps head indoors, pause, and find somewhere cozy to quietly enjoy the upcoming storm. So, if the weather is fair, but you notice rain in the 24-hour forecast, keep a diligent eye on the sky. Your chances of witnessing a magnificent halo will be significantly higher. Of course, the very best way to see one is simply to look up, gently, every single day. Ice halos can form anywhere on Earth, so if you keep looking patiently, you are bound to see one sooner or later. But when it comes to ice halos, there is, truly, so much more to discuss. There are a great many other strange, and even rarer, kinds of halos, and probably many more yet to be discovered. So, if this is a topic you'd like to explore further in the future, and if you have been fortunate enough to see them for yourself, I would love to hear about your experiences in the comments below. The Solar and Heliospheric Observatory, affectionately known as SOHO, recently celebrated its remarkable 25th anniversary in the silent expanse of space. During these 2.5 decades, it has diligently observed the solar wind, kept a watchful eye for dangerous coronal mass ejections, and meticulously studied the intricate atmosphere of the sun. An entirely unintended, yet utterly spectacular, consequence of its relentless observations around this region was the astonishing discovery of over 4,000 sun-grazing comets, the vast majority of which we had absolutely no idea existed, until they gracefully drifted into SOHO's vigilant view. And SOHO isn't the only solar observatory making such serendipitous discoveries. The STERO spacecraft and the Solar Dynamics Observatory have all, in their own right, spotted new comets. And what is so incredibly cool about this, so truly fascinating, is that these observatories were not, in their initial design, intended for comet hunting at all. Today, we will gently explore some of the most impressive of these comets, striving to understand, with quiet contemplation, how they interact with the immense power of the sun, and, conversely, how the sun, in its turn, interacts with them. Sun grazers are precisely what their name implies. Comets that do just that, they graze the sun as they pass. The closest parts of their elongated orbits take them within a hair's breadth of the sun's blazing surface. Often, they will plunge deep into the sun's colossal atmosphere, its corona, a realm of unimaginable heat. These comets are primarily long-period comets, celestial wanderers whose vast orbits can span hundreds, even thousands, of years to complete. Because of the extreme elliptical nature of their trajectories, they build up tremendous, almost inconceivable speeds as they approach the sun, sometimes accelerating to a staggering 0.2% of the speed of light. This is an absolutely incredible velocity for any particle, let alone for an object the size of a house, hurtling through the vacuum. The vast majority of Sun grazer comets, remarkably, all originate from a single, gargantuan comet that was ripped apart by the Sun's immense tidal forces several hundred years ago. This specific group of Sun grazers, often shown in red in scientific visualizations, is known as the Kreutz-Sun grazers. What tends to happen over vast spans of time is that the fragments from the original, larger comet gradually spread out, dispersing along the orbital path. This means there is likely a steady, continuous flow of these fragments constantly approaching the Sun, and as the largest of these secondary comets also pass perilously close to the Sun, they too break apart into even smaller comets, perpetuating the cycle of fragmentation. The reason we believe most Sun grazers originate from this same ancestral comet is simple. They all tend to follow the exact same, distinctive orbital path. The brightest comet witnessed in the last millennium, known as Comet Ikea-Siki, was, in all likelihood, one such fragment. It became so incredibly bright as it approached the Sun that it could even be seen, quite clearly, during the daytime. You may also recall another famous fragment of this ancient comet that, in 2011, dimly illuminated the sky in the southern hemisphere Comet Lovejoy. While Comet Lovejoy wasn't as dazzlingly bright to the naked eye, it did create some truly impressive long exposure images and was meticulously observed by all the Sun-observing satellites then in orbit. Comet Lovejoy was not, by most scientific predictions, expected to survive its perilous encounter with the Sun, as it would have spent more than an hour immersed within the Sun's scorching 1 million degrees Celsius corona. However, astonishingly, it fizzed away from the other side of the solar disk, largely intact, though undoubtedly severely impacted and altered by the experience. A similar, dramatic event unfolded with another comet, Comet Ison. You might remember that Comet Ison was widely anticipated to be an exceptionally bright comet, potentially even visible to the naked eye when it passed by the Sun in 2013. Alas, that spectacular outcome was not to be. Nevertheless, it still provided magnificent viewing opportunities for the Sun-observing satellites. Ison's approach was bright and truly impressive, but upon reaching the other side of the Sun, its brilliance faded dramatically. Scientists cannot be entirely sure if its nucleus survived the ordeal, but if it did, it certainly no longer possessed any volatile, icy substances. All that remained was, most probably, a core of dust and rock. However, these examples, Comet Ikea-Siki, Lovejoy, and Ison, represent some of the largest Kreutz-Sun grazers we have ever observed, their nuclei perhaps being a few hundred meters in diameter. Many of the smaller comets, conversely, were entirely unknown to us until they actually drifted into the vigilant view of a Sun-observing satellite. Due to their diminutive size, often only tens of meters across, many of these smaller comets were completely snuffed out, vaporized by the intense heat of the Sun almost immediately after passing too closely. This means, unfortunately, that they were discovered and simultaneously annihilated almost in the same breath. Sometimes, they will pass around the far side of the Sun's disk, never to re-emerge from the other side. Although, at other times, the precise angle of the comet's orbit allows us to witness this dramatic vaporization as it unfolds in real time. At this extreme proximity to the Sun, the heat is absolutely incredible, and the gravitational pull is utterly overwhelming. The icy comets not only evaporate with astonishing rapidity, but their rocky elements are also violently ripped apart by the Sun's immense tidal forces. Our own close encounters with comets have shown that they tend to be structurally weak and highly porous, sometimes being nothing more than a loosely aggregated pile of rubble held together by its own tenuous gravity. So, combine that inherent fragility with the overwhelming influence of the Sun, and even the largest Sun grazer comets will emerge from the encounter heavily scarred, if they emerge at all. Now, there is an interesting, though currently unexplained, phenomenon that occasionally occurs when a sun-grazer comet passes by the Sun. A coronal mass ejection, CME, will sometimes erupt at the exact same moment the comet is making its closest approach. There are numerous compelling examples of this curious synchronicity. However, scientists are still largely of the opinion that there is no known physical mechanism for a sun grazer, even a large one, to cause a CME. These comets simply aren't massive enough to have any consequential impact on the Sun's internal dynamics. So, it is currently believed that these striking examples you observe are purely coincidental, a fascinating cosmic alignment rather than a causal link. What scientists truly appreciate about sun grazers, though, is their invaluable role as natural probes. While we cannot, as yet, send our own man-made probes deep into the Sun's superheated corona, it is simply far too hot and hostile for our current technology. We do have these thousands of comets that are, in a sense, willing to take the plunge for us, and comets are perfectly suited for observing precisely what we are looking for to better understand the complex magnetic fields within the corona, so that we can, in turn, better predict CMEs and, more broadly, space weather phenomena. Observe, for instance, how a comet's tail subtly wiggles as it passes by. The particles in the tail become so intensely heated that they turn into plasma, which is then easily visible to the UV cameras of our satellites. Plasma, being electrically charged, reacts strongly to magnetic fields. So, the subtle wiggles and undulations you see in the comet's tail are believed to be directly due to the way in which the tail interacts with the intricate, powerful magnetic field lines within the corona. Currently, space weather is a complex domain that we do not yet have a complete understanding of. Thus, as more and more comets bravely pass through this environment, the more we will gradually begin to understand its profound intricacies. So there we have some of the most impressive looking sun grazers caught on camera by satellites that were not even designed to find them. Have you ever been fortunate enough to see a comet with your own eyes? What was your experience like? I'd be interested to hear your stories in the comments below. Have you ever quietly wondered what it would truly be like to have two suns gracing our sky? Witnessing two suns during a sunset would indeed be a spectacularly beautiful sight, a vision of cosmic grandeur. And, in fact, it isn't such a rare occurrence in the grand tapestry of the universe. It is currently estimated that a full third of all star systems in our galaxy possess two or even more stars. This fascinating statistic led me to ponder, how much would the presence of a second star truly impact us here on Earth? How intensely hot would our planet become? What would the rhythm of day and night be like? And, crucially, would it even be possible for life as we know it to survive, to flourish, in a multi-star system? Well, the answer, as with many things in the cosmos, is that it depends. For the purpose of this tranquil thought experiment, let's keep our own familiar sun precisely as it is, and only allow the second star to be the variable, the element we adjust. As we know, stars come in an astonishing array of sizes, from the small, cool, and dim red dwarfs, all the way up to the colossal, hot and intensely bright blue supergiants. In a binary star system, the two stars orbit around a common point, known as the system's barycenter or center of mass. Depending on the individual masses of the stars and the distances between them, you will observe variations in the appearance of these orbits. For stars of similar size, the orbit might appear almost circular or a gentle ellipse. On the other hand, the greater the discrepancy between the star's masses, the closer the barycenter will be to the more massive star. Let's imagine, for a moment, that we gently place a red dwarf, which is the smallest type of star, barely a star at all, into a close orbit around our own Sun. Even though a red dwarf can be as little as 7.5% the mass of our Sun, its presence is already going to have a significant impact on us. From our perspective on Earth, this red dwarf would appear to orbit our Sun, meaning there would be times when it transited, or passed in front of, the Sun, and other times when it was eclipsed by the Sun. Our year, the time it takes for Earth to complete one orbit, would become subtly shorter if we maintained our current distance of 1 astronomical unit from the system's barycenter. This is due to the increased combined mass and gravitational pull of the system from the extra star. Earth's orbital velocity would have to increase to prevent us from being pulled inwards towards the stars. Alternatively, our orbit would have to be slightly further out if we wish to maintain our current velocity. The increase in temperature from this second star would also be noticeably significant, almost certainly making conditions unbearable for humans. But precisely how hot would depend on a variety of complex factors, such as the onset of a runaway greenhouse effect, the intrinsic heat of the red dwarf itself, and more. But let's assume, for a moment, that we could somehow place Earth's orbit in such a precise location that we could, just barely, survive. Even then, our seasons would be massively impacted. The familiar tilt of our planet's axis, which currently dictates our seasons, would become secondary to our fluctuating distance from the second star. When the second star was as far away as possible, and our hemisphere was also experiencing winter, it would become incredibly, brutally cold. On the other hand, combine a summer season with the second star passing as closely as possible, and it would be unbelievably, lethally hot. Additionally, a curious phenomenon associated with red dwarfs is that they are prone to producing enormous, unpredictable flares far larger and more energetic than those emitted by our own Sun. These flares would easily knock our satellites offline on a regular, perhaps daily, basis, and Earth would be treated to spectacular, almost continuous auroras. Our existing power grid, as it stands, would be under serious, existential threat from these stellar flares, as they would act like hemisphere-wide electromagnetic pulse (EMP) bombs. The complex gravitational interactions with this second star could also, quite plausibly, make our primary Sun more active, meaning it, too, might produce more frequent and powerful flares. So, even with the smallest type of companion star, the habitability of Earth, as we know it, would be under serious, constant threat. Increase the mass of that second star, and you begin to encounter additional, even more profound problems. Increased UV radiation, for instance, would make venturing outside more and more perilous. You would also experience two distinct shadows for much of the time. Once you escalate the second star to something truly immense, like a blue supergiant, there really wouldn't be a single place within such a system where there was even a remote hope of habitability. Blue supergiants can be many, many times the mass of our own Sun, with a theoretical upper limit of around 150 solar masses. Their sheer volume is also staggering. They make our Sun look almost puny by comparison. They can be millions of times more luminous than our Sun, too, with devastating stellar winds powerful enough to strip away our atmosphere over a relatively short period of time. Even larger still are yellow supergiants, and then the truly colossal red supergiants. While not necessarily as massive or as luminous as blue supergiants, red supergiants are, by volume, the biggest stars in existence. If you were to gently plop the largest known red supergiant directly into the center of our solar system, it would not only easily encompass Earth, but it would extend outwards, swallowing everything up until the orbit of Saturn. That's a volume 10 billion times greater than our Sun. However, there is one specific scenario where we could exist in a binary star system with a supergiant and still find ourselves on a potentially habitable planet. You see, Binary stars can orbit very, very far apart, sometimes taking thousands of years to complete just one revolution. The most extreme cases can involve binary star systems with a separation of over 1 light-year. What can happen in such widely separated systems is that individual planetary systems form around each of these stars separately. This means that if Earth were to exist within one of these planetary systems, it would effectively have only one primary parent star. Even if that star was part of a binary, the second, distant star would be easily visible in the night sky, perhaps a dazzling point of light. But it might not make much of an impact during the daytime, depending on its intrinsic luminosity. Stellar winds from the distant companion star would have little significant impact on Earth, as our own Sun's powerful magnetic field would effectively redirect most of it away. The biggest problem with having a super-giant on your cosmic doorstep, however, is that it is, by its very nature, a ticking time bomb. Supergiants tend to be stars that are nearing the end of their lives, often on the verge of erupting in a catastrophic supernova. A supernova exploding only 1 light-year away would be, quite simply, cataclysmic, almost certainly sterilizing our entire planet as the intense radiation from the shock wave swept over it. And that's not even to mention the incredibly powerful gamma-ray bursts that would emanate from the resulting neutron star or black hole. In fact, a recent study has suggested that merely being within 50 light-years of a supernova explosion would be close enough to cause catastrophic, life-ending damage. However, the good news, for now, is that we do not know of any star capable of erupting in a supernova within a comfortable 100 light-year radius of Earth. Going back to our single parent star within a binary configuration, here on Earth, with our solitary sun, we experience a beautifully regular day and night cycle. However, should we introduce a second sun, orbiting outside of our own orbit, but still relatively close to us, it would dramatically interfere with our familiar day and night cycle. There would only be tiny, fleeting parts of the year where you would experience a proper, distinct day and night cycle. As the year progressed, you would gradually experience less and less of a true night, until, at one point, you would have no night at all, living under perpetual daylight from 2 stellar sources. So there we have it. While the initial prospect of witnessing a second sun during a sunset might seem like an utterly amazing, breathtaking vision, delving into the intricate details of such a scenario reveals that we are, in fact, incredibly lucky to have only our single, steady sun. No matter what configuration you consider, the presence of a second star introduces a host of major, potentially devastating problems. Be it devastating solar flares, a completely ruined day-night cycle, having a stellar neighbor that might explode into a supernova at any moment, having our entire orbit devoured by the sheer volume of a colossal star, huge, unpredictable swings in seasonal temperature changes, our delicate electronics constantly being fried, or intense, harmful UV radiation, and likely many other unforeseen challenges I haven't even mentioned. In reality, even if life as we know it does exist around binary star systems, those forms of life would undoubtedly have to overcome some major, formidable obstacles to reach a state comparable to ours. So, let us be truly grateful for our boring, perhaps, but wonderfully steady and safe star, the Sun. Long may it continue to be so. Often, on a clear day, I find myself briefly glancing at the Sun, and I am invariably filled with a profound sense of awe at its sheer size and dazzling brightness in our sky. It's truly difficult to fully grasp that it is millions of kilometers away, yet it exerts such a massive, fundamental impact on us here on Earth. Life, quite simply, would be impossible without the Sun. Almost everything, in some way, can be traced back to the light and energy it so generously provides. Even though it is relatively close to us, and certainly not difficult to spot, there is still a vast amount that we do not fully comprehend about our star. This is precisely why both NASA and ESA, our leading space agencies, have in recent years dispatched sophisticated spacecraft to meticulously study the Sun. These missions, representing the closest we have ever dared to venture towards our star, will be able to directly interact with its outermost atmosphere. So, why are we sending these incredibly advanced spacecraft to the Sun? What specific scientific objectives will they pursue there? What remarkable discoveries have they made so far? And what makes each of these dedicated missions so special and uniquely designed for its purpose? Today, we will quietly investigate NASA's Parker Solar Probe and ESA's Solar Orbiter, and explore how these two magnificent craft are dedicated to unraveling the mysteries of our own magnificent star, the Sun. The Parker Solar Probe, a testament to human ingenuity, was first announced in 2009 and subsequently launched on August 12, 2018, atop a powerful Delta IV Heavy rocket. This probe will utilize a series of 7 carefully choreographed Venus flybys over a span of nearly 7 years to gradually shrink its elliptical orbit around the Sun. At its closest, most daring point, it will approach to within a mere 6.16 million kilometers of the Sun, a distance that places it deep inside the Sun's corona, its searingly hot outer atmosphere. To truly conceptualize what being that close would entail, imagine experiencing the heat and light of 500 suns in the sky, all beating down at the same time, with temperatures reaching an astounding 400 degrees Celsius. At these incredible temperatures, many of the components typically used to construct the sensitive equipment for spacecraft would simply melt away. To valiantly protect the spacecraft and all its delicate instruments, it is shielded by an 11-centimeter thick carbon composite heat shield meticulously designed to withstand these unimaginable temperatures. This shield also possesses a wide, highly reflective surface, specifically engineered to help minimize heat absorption. This critical shield will always be facing the Sun, providing an unwavering bastion of protection for the spacecraft in this incredibly harsh environment. Being so far from Earth and orbiting such a dangerous, dynamic object, this spacecraft is, by absolute necessity, as autonomous as any space mission has ever been. For large sections of its orbit, when the heat shield must constantly face the Sun, it will be unable to point its antenna back towards Earth, resulting in periods of communication blackout. During these crucial times, the probe will independently control each of its numerous sensors, manage the intricate formatting of its data products, and diligently archive high-resolution data until it can re-establish communication with Earth and transmit back all that it has meticulously captured. ESA's Solar Orbiter mission began its development journey in 2012, and after 8 years of dedicated effort, the Solar Orbiter was launched on February 10, 2020, on an Atlas V rocket. The Solar Orbiter will also cleverly utilize gravity assists from Venus, as well as from Earth itself. Swing-bys will meticulously guide the Solar Orbiter into an initial 180-day orbit around the Sun. The spacecraft will reach its closest approach to the Sun every 6 months at a distance of approximately 43 million kilometers. This is, comparatively, a much greater distance than the Parker probe's closest approaches. However, to give you a sense of the temperatures, even at this increased distance, at 43 million kilometers from the Sun, the temperature can still reach up to a scorching 500 degrees Celsius, as the sunlight will be 13 times more intense than what we experience here on Earth. The Solar Orbiter is protected by its own heat shield, crafted with titanium foil layers approximately 40 centimeters thick. While not as ultimately robust as the Parker probe's shield, it is still more than sufficient to protect the spacecraft on its dangerous and critical mission. It is, surprisingly, incredibly difficult to launch a probe into a close orbit around the Sun, This is because it takes an astonishing 55 times more energy to send a probe towards the Sun than it does to send one to Mars. You see, Earth is constantly moving sideways relative to the Sun at very high speeds, approximately 30 kilometers per second or 108,000 kilometers per hour. In order for a probe to successfully enter into a close orbit around the Sun, it must effectively cancel out almost all of that immense sideways motion. This is why both the Parker and Solar probes were launched using two of the most powerful launch vehicles available at the time, the Delta IV Heavy and the Atlas V. The primary objectives of the Parker Solar probe and the Solar Orbiter are, to a great extent, quite similar. Both of these groundbreaking missions aim to uncover more about our Sun's enigmatic corona, its pervasive solar winds, the powerful coronal mass ejections, the intricate structure of the Sun's magnetic field, and simply how all of these dynamic phenomena fit together into a coherent whole. The Sun, like all stars, is fundamentally a colossal ball of plasma. Plasma is superheated matter, so intensely hot that the electrons are stripped away from their atoms, leaving behind an ionized gas. The Sun possesses an atmosphere of this extremely hot, yet tenuous plasma, extending outwards for millions of kilometers, known as the Sun's corona. You can observe this plasma atmosphere in captivating images, although typically it is far harder to discern than the Sun itself, as the Sun's visible outer layer, the photosphere, is overwhelmingly brighter. The ideal, most breathtaking time to spot the Sun's corona is during a total solar eclipse, when the Moon perfectly blocks out the brilliant photospheric disk, leaving only the wispy, ethereal arms of the corona visibly shimmering around it. The strange, perplexing thing about the Sun's corona is that its temperature ranges between 1 million and 3 million degrees Celsius, whereas the Sun's visible surface temperature is only about 500 degrees Celsius. And currently, we don't really understand why this dramatic temperature inversion occurs. While the Sun's corona appears substantial and luminous, its brightness is deceptive. It is, in fact, magnitudes less dense than Earth's own atmosphere. The Sun continuously releases huge amounts of plasma and radiation into space, a phenomenon known as the solar wind. This solar wind is not in itself particularly strong or dense, and Earth's powerful magnetic field largely diverts most of it harmlessly around our planet. However, a portion of the solar wind does get funneled towards Earth's magnetic poles, where the charged ions from the solar wind collide with atmospheric oxygen and nitrogen atoms. The energetic interactions between these particles emit the beautiful, vibrant colors we witness in the auroras. The number of particles ejected by the Sun is not constant, it fluctuates dramatically. Powerful magnetic reconnection events within the Sun's magnetic field can release immense amounts of energy in the corona, ejecting millions of tons of charged particles into space in one colossal eruption. This is precisely what is known as a coronal mass ejection, or CME. When these CMEs interact with Earth's magnetosphere, they cause what is termed a geomagnetic storm. And the biggest of these storms can be truly devastating. The largest geomagnetic storm ever to directly impact Earth was the Carrington event, which occurred back in 1859. If such a CME were to strike Earth today, the resulting storm could severely affect satellites and our entire electric power supply, potentially acting as a hemisphere-wide EMP bomb. As we depend so profoundly on electricity and the internet, even a few hours of widespread outage could cause serious, cascading problems. Some estimates suggest that if a Carrington-sized event happened today, it could cause trillions of dollars in damages and, unfortunately, CME flares are incredibly fast. They have been observed to reach Earth in as little as 17 hours. This might not be enough time to alert the entire population, power down critical reactors, and take all necessary precautions. In reality, we have, up until this point, simply been incredibly lucky. we narrowly missed a Carrington-sized event hitting us by a margin of just 9 days in July 2012. Had it been 9 days later, Earth would have been a bit further along in its orbit, directly in the CME's path. This is precisely why it is so critically important for us, as a delicate, technologically reliant species, to profoundly understand the Sun's corona. This deeper understanding will allow us to better predict solar storms, giving us crucial, extended warning times, and hopefully enabling us to avoid the catastrophic damages associated with a Carrington-sized event actually striking us. It is, truly, just a matter of when, rather than as if. Now, these two pioneering probes, the Parker Solar Probe and the Solar Orbiter, may seem quite similar in their overall objectives. And while many of their goals do indeed overlap, they each possess some unique features and capabilities. The Parker probe is venturing deep into the Sun's corona, a realm where no man-made object has ever gone before. Because it must withstand such incredibly high temperatures, the spacecraft is, understandably, limited in some ways. For example, it cannot take direct pictures of the Sun, as no current camera technology could look directly at the Sun from that close proximity and survive. However, the Parker probe carries specialized instruments that can directly sample and collect data about the particles that exist within the Sun's corona, and even closely study the very regions where the solar winds originate, something that simply cannot be done effectively from a distance. The Parker probe is also lighter, smaller, and carries less equipment compared to the Solar Orbiter. The Solar Orbiter, on the other hand, carries both particle detectors and powerful telescopes. It can capture close-up pictures of fascinating solar landscapes. And due to its unique orbit, it will be able to track a specific region of the solar atmosphere for a much longer duration than is possible from Earth. This extended observation period will enable it to meticulously observe solar storms building up in the atmosphere over several days. So, as you can see, these two probes are wonderfully complementary, and both will significantly help to further our understanding of the Sun's corona, each in its own distinct and invaluable way. So, what have these groundbreaking missions achieved so far? Well, on September 27, 2020, the Parker probe made a historic pass within 13.5 million kilometers of our star, the closest any spacecraft has ever been. It also, in that moment, became the fastest traveling human-made object ever, reaching an astonishing speed of 466,000 kilometers per hour. And this isn't even as close, or as fast, as it is ultimately going to get. Yet, even at this distance, the data sent back from the Parker probe is already profoundly helping our understanding of how the Sun's magnetic field and the corona interact to form the powerful solar winds. The probe also made the fascinating discovery that some magnetic fields from the Sun sweep through the solar atmosphere in a peculiar way, which can dramatically increase the solar wind speeds by as much as 500,000 kilometers per hour. In addition, it has discovered compelling evidence of a dust-free zone, approximately 5.6 million kilometers from the Sun. It is believed that this phenomenon is due to the complete vaporization of cosmic dust particles by the intense radiation emanating from the Sun. The Solar Orbiter has already sent back its first incredible images of the Sun, and scientists found something entirely new and intriguing, which they have termed campfires. You can observe them here. These are tiny, miniature explosions on the Sun's surface that occur as a result of subtle disturbances in small magnetic fields. The Solar Orbiter also captured the closest images, to date, of the Sun's surface from an existing distance of 77 million kilometers away, and its ongoing examination of particles across its orbit will continue to help us understand the different types of space weather that originate from our star. The Sun is truly a giant, bright, celestial object, a colossal sphere of intense nuclear energy. It ceaselessly unleashes billions of tons of electromagnetically charged plasma, hurtling into space every single day. These violent, breathtaking eruptions, known as coronal mass ejections, or CMEs, shoot off into the vastness of the solar system, causing what we know as powerful solar storms. These highly charged plasma particles race towards Earth at incredible speeds, often exceeding 1,000,000 kilometers per hour. One might, quite understandably, think that with such speed and intensity, we should all immediately head for the bunkers when they arrive. However, our Earth possesses natural, formidable protections in place, designed to prevent most of these energetic particles from reaching us. One such crucial protection is Earth's powerful magnetic field, which acts like an invisible shield, pushing the incoming particles around the planet and deflecting them towards its poles. Particles that do manage to penetrate the atmosphere are absorbed, providing the energy that subtly drives the climate on our planet. In fact, the sun is absolutely crucial to life on Earth. For example, it provides precisely the right amount of warmth and light, allowing plants to photosynthesize, converting the sun's energy into usable carbohydrates. This energy then makes its way down the intricate food chain until it reaches us humans. We consume and convert food to provide us with the energy our bodies can use. Almost all food energy can ultimately be traced back to the sun, our life giver, the very beginning of our terrestrial food chain. But could this giant of our solar system also, paradoxically, create catastrophe? How truly immense can these CMEs become? What if the largest solar storm of all time were to strike Earth tomorrow? Could the sun, in its raw, untamed power, actually damage or even destroy humanity? For a star, our sun is, thankfully, relatively stable. It is a type of star informally known as a yellow dwarf, firmly in its middle age, and it has not changed dramatically in its output or behavior for the last 4 billion years. We can be profoundly glad that our sun is as stable as it is, as unlike most other stars, the energy it emits is remarkably constant. If one were to gaze upon footage of the sun taken by the Solar Dynamics Observatory, however, you would quickly realize that even one of the most stable types of stars possesses a dynamic, ever-changing landscape of activity. Sunspots, solar flares, and graceful coronal loops are present every single day on the sun's surface. One might even say the surface appears almost fluid. But the sun is neither solid, liquid, nor gas. It is rather a giant, nearly perfect sphere of plasma, composed mainly of hydrogen and helium. And at the very center of the sun, due to its enormous, crushing mass, nuclear fusion takes place within the sun's core. Here, hydrogen atoms are fused together under immense pressure and heat to become helium. The sun itself, I tend to think of it as an onion, essentially consisting of different layers. So, in the core, the very center of the sun, that's essentially where nuclear fusion happens. Now you have to think, essentially the sun is a kind of huge bowl of plasma, a soup of particles, ions, atoms, electrons, sort of everything mixed up together. On average, it takes a photon, a tiny particle of light, to travel through the radiative zone, something like 170,000 years. It's basically incredibly dense. And then from that, it then hits the convective zone. Everybody knows that hot air rises and cold air falls. So what then happens is the material is very hot at the bottom, near that radiative zone. And then it expands and it rises to the surface. And that's the main transfer of heat from that point onwards, obviously then glowing from the surface, like any hotter material does. Plasma is an extremely good conductor of electricity and is also strongly affected by magnetic fields. So sunspots are actually the surface representation of the magnetic fields of the sun. The magnetic fields actually get very tangled below the surface, so between that radiative zone and the convective zone, the magnetic fields get tangled. They tend to appear in pairs, in groups. If you think of a magnet, you have a positive polarity and a negative polarity. That's sort of normally seen in a sunspot pair. One would be positive, the other would be negative. And normally the strongest magnetic fields that we observe are in the sunspots. Sunspots can be anywhere from about 15 kilometers in size to around 160 zalozhen kilometers, so multiple times the size of the Earth. Sunspots can often be seen at the base of various other solar phenomena, coronal loops, those large, graceful rings of plasma in the Sun's atmosphere, prominences, those large, bright, gaseous features extending outward from the Sun's surface, bridging into space for thousands of kilometers, and solar flares, a sharp, dramatic increase in the Sun's brightness and temperature. Solar flares tend to happen over active regions, and active regions are essentially sunspot groups. So these are the locations where we definitely see the strongest flares. A reconnection event is essentially what produces the energy that causes both flares and CMEs. Because the convective zone is essentially very turbulent, many of the current simulations show that most of the magnetic field, as it rises through the convective zone, is basically being destroyed, diffused around. It's more complicated magnetic structures, such as twisted magnetic fields, that tend to survive. So you can imagine, especially over large sunspot groups, we do see very complex magnetic field configurations, magnetic fields so twisted, braided, basically creating these complicated geometrical, topological structures. And it's within those structures that magnetic fields and magnetic energy are stored. And what happens during reconnection? I tend to describe it like thinking of the magnetic field as a rubber band. So you twist it, turn it, and then basically at some point, you pull it too strongly, and it breaks. And that's essentially when we have the reconnection event. And what happens during the reconnection event? Essentially, as the name suggests, the magnetic field lines reconnect. And when that happens, you get a lot of energy being released, on the order of millions of nuclear weapons, nuclear bombs, all in one instant. And that energy will produce both solar flares, where large amounts of radiation are released, and also potentially lead to large-scale movement of the material that was suspended in the prominences, both towards the Sun and away from the Sun. When that reconnection event happens, then again, the material which is suspended in those magnetic fields normally will move one way or the other. A lot of it will move back towards the Sun, often following those magnetic field lines, so moving to the footprints, like for instance, moving to the sunspots, if that's where the footprints are. But equally, in the middle of those magnetic fields, quite often a bubble of material is essentially ejected away from the Sun. And so what you'll end up having is millions of tons of charged material flying out from the Sun relatively fast. On the order of hundreds of kilometers per second to thousands of kilometers per second. And those are what we call CMEs, coronal mass ejections. These CMEs come into contact with the planets all the time. Venus, when faced with a CME, has its lighter particles stripped away in the higher reaches of its atmosphere by the sheer force of the ejection. This leaves the planet with just the heavier molecules, forming a toxic smog that cannot, as far as we know, sustain any life. Earth would face a similar, devastating fate if it weren't for its relatively strong magnetic field. Particles from a CME aimed at Earth are largely redirected around the planet because of Earth's magnetosphere. Some particles do get redirected to Earth's poles, where the charged particles collide with the Earth's ionosphere, causing the beautiful auroras we discussed earlier. Thanks to a combination of Earth's magnetosphere and its protective atmosphere, we are generally well protected from all sorts of energetic particles space likes to throw around.